So last class we talked about what is a sampling distribution. And last unit we talked about binomial distributions and the patterns we see in binomial distributions, and how if we have a binomial distribution we can find the mean and the expected value. And so what we're going to see is something kind of interesting here, which is we're going to put a bunch of theory together and use it to describe the sampling distribution of p hat. So by the end of this video you should be able to find the mean and standard deviation of a sampling distribution of a sample proportion. Right? The value of the sample proportion we'll refer to as p hat. Determine whether or not it's appropriate to use the normal approximation to calculate probabilities, and then calculate those probabilities and evaluate a claim about a population proportion using the sampling distribution. This we will mainly do in class. But we need to get the theory out of the way first, so let's do that. So the whole idea of a sampling distribution was how good a statistic is that p hat is an estimate of the parameter p. And the sampling distribution of p hat answers this question. And so what we have here is a model where they generated many simple random samples of Reese's Pieces from a machine. And they got it. And right here, this is the true proportion. So in this area, the proportion of, I think they used orange candies, was 0.15. And it took a sample and it got a p hat of 0.24, and so it plotted it. And it kept plotting it, and it kept plotting it, and it kept plotting it, and it kept doing all these things. And it's never going to, and it did it with sample size 25. And so it plotted all of them. But if you notice, if you keep doing this, and unfortunately it's an applet that will not run at the school, but if you keep doing that, what you get is this shape again. And what's really interesting is the center of that shape is the 0.15. And so when we look at sampling distributions of p hat, we'll see that they're going to be approximately normal in some cases. In some cases, they'll be approximately normal. And whether they're normal or not depends on the sample size and the proportion. We'll talk about that later. But the center, the mu of p hat, will be p. So the center of the sampling distribution is the true value, the true proportion of this. And that's true because it's an unbiased estimator. And the spread will depend on a couple of things. It'll depend on both n and p, but a lot on n. So but the spread of the sampling distribution will be sigma p hat. So what we're going to do is let's put together some stuff we talked about. So we calculate p hat would be the number of successes and the sample size. And so we get p hat equals x over n. And this should look, but what's really interesting is that if I multiply both sides by n, I get n p hat equals x. And that should look vaguely familiar from our time as a binomial. Because if you remember, the binomial said that the mean of x was n times p. That was our expected value of a binomial. And so things start to overlap. Because if you remember, we made the discovery that we could approximate a simple random sample without replacement using a binomial probability as long as we sample less than 10% of the population. And we did that. We did the math. We did the crazy conditional probability. And then we did it with a binomial, and we saw that the difference was only like the 5th decimal place. And so if we replace this with the binomial, then we can use the binomial rules. We know that the mean of x equals n times p. And so the mean of p hat is 1 over n times p. Because we just said n times p hat equals x. Well, in this case, n's cancel. And so what you end up with is the mean of all p hats is p. And that's really the one we need to worry about. And then we saw that the standard deviation of x in a binomial distribution was n times p times 1 minus p. So the mean of p hat is going to be 1 over n times n minus p. And then when you smush the n squared in, the n inside the radical becomes n squared. And so we get this. So the standard deviation of p hat is the square root of p times 1 minus p over n. And that's very important because right here the standard deviation is going to be largely determined by the sample size. The larger the sample size, the smaller we're dividing by it, so the larger this number gets, the smaller the standard deviation. Now it's not a 1-to-1 ratio, it's inside the square root, and we'll discuss that in class 2. But what this means is that for all values of p hat, it's going to follow a distribution where the mean is the true proportion and the standard deviation is the proportion times 1 minus the proportion divided by the sample size, and you take the square root. Which is interesting because if you also remember, whoops, wrong way, is that we made the rule that if n times p was greater than or equal to 10, if the number of successes and the number of failures in a binomial were both greater than 10, then our distribution became approximately normal. Now we're getting into the who cares about this. But now, if we go back one, that means that as long as n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then this is a normal distribution. And then I can start doing what's my probability of winding up in this area. And the only thing I need to know is what the true proportion of the population is and what the sample size is. And we start to get some very, very interesting results from that. So you have to have this. Right? We have to have this. So, in review, mu p hat equals p, and sigma p hat equals p times 1 minus p, the square root of that. And as long as these two numbers are greater than 10, then the distribution is approximately normal. And now, for the sampling distribution, we have the center, we have the spread, and we have the shape. And there's no unusual values because it's approximately normal.
Nathaniel Swanson, if you're in the building, please come to the main office. Nathaniel Swanson, if you're in the building, please come to the main office.
So there you go. Nathaniel Swanson wasn't where he was supposed to be while I was recording this video. So what we're going to do then in class is we're going to take this and we're going to start applying these problems and putting them together to do that. But now we need to have those formulas for what is the sampling distribution of p hat. So in the next class.